evening, everyone. Welcome to Network Seminar Series hosted by CNI, Center for Networked Intelligence at the ECE and RBCCPS IISc. It is my pleasure to introduce today's speaker, Professor Namrata Vaswani. She will be speaking on mathematical ML and ML for math, alternating GD and minimization for secure federated low-rank matrix learning for real-time MRI and ML-enabled K-12 math support. Professor Namrata received her PhD from the University of Maryland, College Park in 2004 and her BTech from IIT Delhi in 1999. She has been with Iowa State since fall 2005 and is currently the Anderlik Professor of Electrical and Computer Engineering. Her research focuses on data science, particularly statistical machine learning and signal processing. She directs the SciMath K-12 math tutoring and support program. She has served as associate, area, and guest editor for leading IEEE journals and served on the SPS Board of Governors, including as chair of Women in Signal Processing. She is a recipient of multiple research awards and is an IEEE fellow and AAAS fellow. Over to you, Professor. And served on the SPS Board of Governors, including as
Thank you so much for inviting me, and thank you, Chandra and CNI, for hosting the talk. Is the audio good for you? Folks at the back can hear clearly? Okay. Okay, so I'll tell you a little bit about AltGDmin. I should mention this is joint work with a lot of current and now former graduate students. Dr. Sayede Sara Nair started this AltGDmin work. Ankit is my student who will graduate soon and eventually wants to teach in India. Looking for postdocs right now. Dr. Abbasi just graduated, works for Amazon, and Dr. Shilpa Babu is also just graduated, working in MRI as a postdoc and looking for full-time positions. Here is a brief outline, but basically item 2 is the longest. The rest are, I'll touch upon the rest of my work just to give a broad overview of what I do. Yes. Oh, yeah. So this, okay. Good, thank you. Yeah. So let's see. I'll just start with a quick introduction. Is everyone here familiar with federated learning? Probably, right? So just to set the setting, we're considering simple traditional federated learning where you have multiple nodes talking to one center. The goal is to collaboratively solve a machine learning problem. Different subsets of data are available or captured at different nodes. And each node can only communicate with a central server or service provider, which we'll refer to as the center. Two key concerns in federated learning. One is communication efficiency. In fact, it's a concern not just for federated, but also for any distributed algorithms. Sometimes raw data privacy is an issue also. And then the other main issue is resilience to attacks by adversaries, and especially model update poisoning attacks. And even within that, the Byzantine attacks are the most difficult class of attacks to deal with because they're the most general. Quick review of low rank matrix learning. Once again, let's just to get a sense of how deep I should go. Does everyone know what low rank matrix recovery? Okay, so yes and no. Okay, so let's talk about it. So the goal in low rank, so I'm just using learning because it's a cooler word, but it's low rank matrix recovery. You want to recover an n cross q matrix which has rank r that's smaller than the matrix dimensions, much smaller than the matrix dimensions. And the point is that if the rank is much smaller, you should need less than nq samples to be able to recover it correctly. The question is, when can you do that? And the other question is, what are the settings? Sometimes you have deliberately undersampled measurements, like an MRI. And in MRI, you have column-wise undersampling. You might have incomplete data, which is the matrix completion problem. You might have outlier corrupted data, which is the robust PCA or robust matrix completion problems. Or you have the phase retrieval setting where you have entry-wise nonlinearities. So essentially, you have bad measurements of an unknown low rank matrix, and you want to recover the matrix from that. why is low rank a good model? A lot of natural data sets, anytime there is time series, vector time series data, are well modeled using the low rank model because it's a very weak model. All it's saying is the images, for instance, a lot of image sequences are modeled as low rank. What it's saying is images change slowly over time, roughly speaking, or really more precisely, the number of changes in the image, the changes in the images can be quantified by only R linear factors, where R is much smaller than the matrix dimensions. MR image sequences are commonly modeled as low rank. Videos are well modeled as low rank plus sparse, with the foreground denoting the sparse component and the background denoting the low rank component. Product rating matrices or product rating tensors, if there's multiple products, are often modeled as low rank. And then correlated regression coefficients in multitask learning is another instance of an LR matrix. And then more recently, what I'm hearing, this is not something I'm working on yet, is LLM fine-tuning. The changes in weights are also often modeled as low-rank matrices. So each weight layer, and I think it's called low-rank adaptation. And then in this particular talk, we are primarily focused on the federated setting, although the algorithms work in the centralized setting too. And the federated setting we consider is subsets of columns of X star are sensed or measured at different nodes. So vertical federation. Yeah. Oh, yeah. I think it's because of the mic or? That's. Is it better now? Okay. Good. Huh? Huh? Yeah. Yeah. Hari gave me a different reason for it, which we'll talk about offline. So what we have developed or rather we have studied it, probably versions of it existed various places, but we've studied it actively for certain classes of problems, is the alternating gradient descent and minimization solution. Algorithmically, it's a very minor modification of AltMin, but I'll explain why it's useful and how it's useful and where it can be used. So the most common, if you want to solve a general non-convex optimization problem, the most well-known solution is gradient descent, or its 100 modifications, stochastic GD and its various modifications. I just wrote simple gradient descent here. Your new iterate is the current iterate minus a step size multiplied by the gradient. Works for any, in principle, it works for any you can implement it for any differentiable function f, but the problems are, depending on the step size especially, it converges slowly, or sometimes may not, depending on the problem at hand. But the advantage of the reason why people have returned to basic GD as against Newton's method and all those other things is the per iteration cost is very low. Then there is alternating minimization, which is a special case of the block coordinate descent class of methods, where you're typically using it, or at least the settings where it has been extensively studied theoretically also, is if you can split your Z into two disjoint subsets ZA and ZB, so that minimization over ZA, keeping ZB fixed and vice versa, is either closed form or otherwise reliably solved. And in that case, you run these two iterations. You fix one, minimize over the other. At each main algorithm iteration, you're running this. This is one iteration, right? You're updating, you're fixing ZA, updating ZB, then fixing ZB, updating ZA, and repeating this multiple times, starting with an initialization of ZA, right? The advantage of this is per iteration cost, when it can be used, it converges much faster than gradient descent, or you can prove it converges for certain classes of problems. But then the per iteration cost is high because you're solving a full minimization at each, two full minimizations at each iteration. Now, what happens for certain classes of problems is that one of the two minimizations may be decoupled, whereas the other is coupled. So only one of the minimizations is taking most of the time, right? If the minimization is decoupled, it's already fast. So our idea, which came from first solving this particular problem called low rank column-wise sensing, is that for problems where you have this structure, and a lot of low rank problems are like that, you can actually replace one of the minimizations by a single gradient step. So essentially, it's AltMin with one of the minimizations replaced by a gradient step. That's it. And then problem-specific modifications needed to prove guaranteed convergence. What this buys you for, again, not all problems, but these classes of what I call partly decoupled optimization problems, is you get the per iteration cost of gradient descent often, because the other minimization is very fast. And you can prove convergence at almost the same rate as that for alternating minimization. So you get the best of both worlds. In short, what you get is improved either overall speed and or communication efficiency. So that's like the whole talk in one slide. So if you want to go to sleep now, this is a good time. Or just listen to the next 3 slides so you get one concrete example of what I'm saying. And the rest is all details. So yeah, here is the low rank column-wise sensing problem, which is actually one of the lesser studied. It's not as popular as matrix completion or full matrix sensing. So here, what you're doing is you have compressive measurements, linear compressive measurements of each column of the matrix X star. Classic application is MRI, where my X star K is my kth image, and I have partial Fourier measurements of each column. The matrices AK are known M cross N matrices. Obviously, the setting of interest is when M is much smaller than N. And again, I should point out any low rank matrix X star can be factored as U times B, where U, the inner dimension is R. So U is N cross R and B is R cross Q. To keep it concrete, we'll assume U star is orthonormal. So it's the matrix of top R singular vectors of X star. And B star is the rest. And again, I'll reiterate, federation in our case means different columns YK are observed at different nodes. So notice here, this is the one asymmetric low rank problem where vertical federation is different than horizontal federation. Both matrix completion and the standard full matrix sensing are symmetric. Applications, MRI is the most important application. There is potential applications in sketching, federated sketching. There is also potential applications in what's called multitask learning, essentially multiple linear regression models with correlated coefficients, and using it for few shot learning or meta learning as it's called. In old language, we would call it subspace tracking, but again, same idea, different words in ML. So here's the algorithm. So notice this is a problem. This is actually where we came up with this AltGDmin solution, because we were trying to look for gradient descent-based fast solutions for this problem. So here is the cost function. If you're factoring your unknown x as u times b, here is your cost function. You're writing your xk as u times bk. So notice from here that you have decoupling over, excuse me, here, you have decoupling over b. So bk, column bk only appears in the kth term of this summation, whereas u appears in all the terms. So this is the classic example of the asymmetric problem I was talking about. And a most efficient and provably correct solution here is to do the following. You initialize u, I'll talk about that on the next slide, and then you alternate between minimization over b. This is what you need to do, but clearly because of this form of this cost function, this decouples as q very small dimensional low rank recovery problems, right? So the dimension of this AK times U matrix is only M cross R. M is my number of measurements per column, so M is small. R is my rank, so R is even smaller. What we'll prove is that M, if you have a square matrix, then M of order R square suffices. So M is a small, right? So what happens is that this, and then you're doing, because updating U is the expensive part, what you can show is that the gradient computation over U has the same cost as doing all these Q least square steps, right? So essentially, you're getting minimization for free. And the idea of this algorithm came about because AltMin for this problem was slow. In past work, Sarah and I had looked at the alternating minimization solution for this LRCS problem, which was updating U was the bottleneck. Coming to the initialization, so if you've seen low rank work, you'll understand this, that the typical approach to initializing a low rank matrix is to look at the adjoint operator. In this case, it is AK transpose YK. And what you can show is that its expected value is essentially a scalar m times the column x star k. So essentially, AK transpose AK has expected value identity, or constant times identity. So that's why the first attempt to initialize would be to compute this matrix, which I call x naught full, which is this thingy, and try to compute its top R singular vectors and hope that they are a good approximation of the top R singular vectors of my x star, which is essentially my U star. So you want an approximation in subspace of U star. So that's what you would do if you followed standard protocol on what is studied in the literature. But notice here there is a problem. What happens is that yes, in expected value it's true, and you would hope that x naught full, if MQ is large enough, so if you have enough samples, law of large numbers kicks in, and x naught full is also, you can show that it's a good approximation of x star. Just because expected value is equal doesn't mean, just because it's unbiased doesn't mean it's a good estimator. And you should be able to, if you can prove this, then you can also prove that the same is true for their column spans, right? Column spans of their top R singular vectors are also similar. But notice what happens is that if you try to write, here, x naught full as a sum of scalars, vectors, and Ek is my kth column of identity. If you try to write it as this summation, what you see is that the summands are sub-exponential random variables with worst case sub-exponential norm being very large. Not something you can see immediately from here unless you've worked in this area, but in short, in simple language, the summands are very heavy-tailed, which means a few large YKs can bias your average a lot. Or a few large YKIs can bias your average a lot. The fix is to borrow a truncation idea used in a different context in a Candace-Chen paper, the phase retrieval paper. Here, truncation means just throw away not the YKIs that are too large, right? So the idea is sum over only the not too large YKIs. And mathematically, what it's doing is it's taking these bad sub-exponentials and converting them into sub-Gaussian random variables. The Candace-Chen paper used truncation to convert something that was heavier tailed than sub-exponential to sub-exponential. So this is the key that makes our initialization actually nicer than one of the parallel works. Again, a very simple idea, but yeah. So yeah, yes. So the word truncation, that's what the Candace-Chen paper called it, truncation. So this is what you're doing. So here is the math of what you're doing. So you're, instead of, remember in the previous slide I had AK transpose YK. Now I have a new vector which I call YK trunk because they call it truncation. What it's doing is, it's taking each entry of YK, checking if it's larger than a threshold, then zeroing it out. If it's below, and the threshold is computed based essentially the mean squared, square root alpha is the RMSE value of all the entries. Right? So you're taking YKIs, so there's MQ YKIs, squaring them and taking their average, and square root of that alpha is my threshold. Right? Or C times, sorry, there's a constant, I'm sorry, there's a constant C which comes from theory. And using that as a threshold. Yeah.
But somehow you're dropping that to 0. What's the impact of that? I mean, the other one would be projection to.
So the hope is that you're not dropping. That's what you're proving. You're proving that you're not dropping too many entries, because very few. So Remember this, and really, frankly speaking, this is a theoretical issue. It's not a practical issue. Practically, when you're simulating data, the likelihood of seeing those really bad entries is very small. But when you want to prove a high probability result, all you're saying is the worst case sub-exponential norm can be very large, right? So in simulations, my student has sometimes, when forgotten to do this or whatever in the first few simulations, it still works the same. So it's maybe if you ran like 100,000 trials, maybe in one trial it causes a problem. I think it's an artifact. That said, even the proofs are high probability guarantees, but yeah, it's still an artifact of the proof, primarily, I feel. The rest of it, other than the truncation, and again, in the MRI, when we apply this to MRI data, we are applying it to partial Fourier measurements where there's where this issue goes away, actually. So this is an issue for random Gaussian settings.
Yeah. Federated learning, the min for B is something you would do at the individual nodes, and the min for U has to be done at the centralized.
Precisely, and that's why we get, we started off not studying federated learning at all. We started off designing a fast gradient descent based solution for this problem. We get communication efficiency for free. And then we have used this also for matrix completion, where the only advantage is exactly what you said, communication efficiency for free. So matrix completion is decoupled column-wise and row-wise. So AltMin will be the fastest central solution, right? But AltMin, if you want to implement it in a federated or any just distributed learning setting, it will require a lot of data exchange, because you'll be doing a whole set of gradient descent iterations at each main loop iteration. Right? So, and yeah, you're absolutely, yeah, so that's the next slide is exactly saying that. So here's your complete algorithm. Here is the initialization I was talking about. Right? How are we doing on time? Okay. Then you're orthonormalizing U, which is also, well, it has two advantages. One is it's needed for the proof. Second is it lets you set your step size. Even in experimental work, it lets you set your step size once and not have to worry about it, because, yeah. And then exactly what Chandra predicted, you're getting communication efficiency for free, because you can be updating your BKs locally at the node at which YK is available. You compute your partial gradient, transmit it to the center. Center will do the sum them or average them depending on how you want to write your step size, and orthonormalize and do the rest. So per iteration communication cost is only NR, and there is only one loop of data exchange per algorithm iteration. And time is MQNR per iteration again. So basically, for this particular setting, there's nothing extra you need to do to design a federated algorithm. You get it for free. Are there any questions first, just on the algorithm? Yeah, sure.
So here for the decoupling to work, you kind of need the loss function to have that special structure, right? In this case, quadratic you have. So like, is there a way to, how does MSE or something like that?
Here, no, it's not the quadratic part. Here, it's the fact that BK appears in only the kth term. Right, so I'll show you some examples, all of which are from low rank. There's one other example I know, which is permuted sensing. So there's a couple of classes of problems where this would apply. Right? So the class of problems I would look at is where AltMin has been used, but one of the steps is, or both of the steps are slow. Or even if both of the steps are fast, sometimes for communication efficiency, this is better than AltMin, because in AltMin you're having to, if you have to do a full minimization over U, you are having to share a lot of data at each iteration. So that's why for all problems except this problem, you're only getting, the main advantage is communication efficiency, not speed. And hence the talk title. And then the other advantage in Byzantine resilience is because, again, essentially at the top level, all you're doing is you're replacing, you have one gradient descent step and a couple of things done locally. So the entire literature from Byzantine resilient gradient descent or Byzantine resilient SGD applies automatically. Right? Algorithmically, if you wanted to replace GD by SGD, you could do it and also. Right? So, yeah. So, yeah, so here is what we can prove. So you assume what is called mu incoherence of the right singular vectors, which is roughly saying that, yeah, this is the assumption, mu incoherence. Each signal x star k has roughly similar energy. No signal has energy that's too large. So you're assuming this, and you're setting your step size. It doesn't have to be 0.4. It could be any c between that is strictly less than 1. Your number of iterations is log 1 by epsilon, so there's exponential error decay. The number of samples you need is, okay, I'm treating kappa, which is the condition number of the rank R condition number of x star, and mu as constants, which is again a standard thing. Then the number of samples you need is only a little more than NR, which is the minimum you would need for recovering U star. NR times larger of R or log 1 by epsilon. Right? And under this assumption, you can prove exponential error decay, which is to say you get converge to whatever epsilon you want in order log 1 by epsilon iterations. And for each column of xk, again, you can prove epsilon accurate recovery. All of this is with high probability, right? And the time complexity is this, communication cost is this, sample cost is this. Right? Yeah. Yeah, yeah.
Calling it mu incoherence of the right singular vectors.
Uh-huh.
Condition on the column norms of x.
I wrote it on purpose that way. So you could write it for singular vectors. That's a stronger requirement. So x star k is just the singular values matrix times the right singular vectors. So you could write it for the right singular vectors, which is the standard well-known assumption from LRMC literature. But all we need is, so that automatically implies this assumption. Right? So if you have a, do you get what I'm saying? Here.
X is your n cross q matrix whose rank is R, and x star k is its kth column or not?
Yes, that's correct.
Huh.
So x star I'm writing as u star times sigma star times. For a moment, bear with me, I will write v star, not v star transpose, okay, just for notational convenience, right? So v star transpose is now my v star, right? So right singular vectors are columns of v star. V star k is the kth right singular vector, right? So I can assume v star k square, which is the normal matrix rho norm, mu squared r by q, and that tells me that if I look at sigma star v star k, which is my or u star is just u star sigma star v star k, that is times the maximum singular value of this, which is what I'm denoting by sigma max, right? So right singular vector incoherence actually implies this, right? This has a more intuitive meaning, which is easy to write without the SVD. And this is the only thing our proof actually uses.
Thanks.
Thanks. Other questions? Right. Okay. Good. This is this. Now explaining why new GD-based approach was even needed here. First, it's clear AltMin is expensive because U appears in all the terms. Sorry, here. Because U is not, the problem with respect to U is not decoupled. The main reason, so there's two existing gradient descent based solutions that are commonly used in the matrix recovery, low rank matrix recovery literature. One is projected gradient descent, which is you are running a step of gradient descent for x followed by projection onto the space of rank R matrices using an SVD. First, this is slow, but the other problem is because of this projection step at each iteration, you are getting coupling between the estimates. I'll explain what that actually means. Whereas the other commonly studied solution is what's called factorized GD, which is you write your x as u times b, but alternatively update u and b by gradient descent. Here, to make sure you don't get, you need a norm balancing term to make sure you don't get numerical issues. So you are essentially running gradient descent for this modified cost function. Here too, because of the gradient with respect to this second term, you get coupling in your estimates, which is to say your estimates x, so your estimates of b, my bk's depend on the entire matrix, and I can only bound x, big X minus big X star norm. I cannot get a tight bound on the column wise norm, xk minus x star k. But this tight bound is actually critical in getting a tight bound on the gradient of this cost function. I have not written it to keep it simple. And again, to prove gradient descent error decay, you need a tight bound on the gradient and show that that bound decays over time. So that's the reason. So basically, the problem is decoupled. The algorithms, the xk's are not decoupled, whereas in our case, if you keep u fixed, the bk's are decoupled. The updates of bk's are decoupled. So you get, you're able to get this column-wise bound structure, right? Okay. And here's a comparison with existing work. So there was basically since, so we've studied an AltMin solution to this problem since 2018 or 2019. There was a NeurIPS 2019 paper from Justin Romberg's group which studied a convex relaxation for this problem called mixed norm minimization. Convex relaxation is of course always much slower because there's a 1 over epsilon dependence on in terms of time complexity. And there's a 1 over the sample complexity also, it was designed for the noisy setting, but in the noise-free setting, the sample complexity had a really bad dependence on epsilon. The AltMin solution, sample complexity is good. Time is a problem again, and communication is also a problem. Communication is always a problem for AltMin because you're having to exchange a lot of data. Factorized GD and projected GD, as I explained, do not work, so you cannot come up with a sample complexity. The time complexity is what would have happened if they did work, but yeah, so essentially projected GD is also very slow. AltGDmin has these advantages. Disadvantages, it needs sample splitting. Factorized GD, if it could be used, does not. Okay. I think, okay, briefly the proof uses, I can explain, I have a few slides on the proof, but I think I'll postpone those to one-on-one discussions if we are interested. But at top level, the proof needs you to know the Weiden or the Davis-Cahan sine theta theorem, which is essentially bounding, looking at the error between two matrices and using it to bound the error between their top R singular vectors, the subspace distance between their top R singular vectors. And you're using the Verschijnen book or the Verschijnen tutorial. So a lot of concentration bounds, probability concentration bounds that I learned from Verschijnen. I don't think they're all his original results, but he's provided it in a way that's easy to read and understand. So you're using the sub-Gaussian. So for initialization, most of the work was in the algorithm designed to convert it into an easy problem. After that, it's standard techniques. Update of B, again, once you have come up with this update solution, you can show things fairly easily. Update of U, you're using this subspace bounding technique, which is you're taking your U plus, projecting orthogonal to U star to get a subspace distance measure like this, using this fact to get this, expanding this out, And then using the fact that the expected value of the gradient is this simple thing, is x star minus x times b transpose. And if you project this orthogonal to u star, then this first term goes away. That's the critical part. And that's what gets you a nice expression that can be shown to decay. And then you're essentially taking this, what I call diff, which is the gradient minus its expected value, and using sub-exponential Bernstein to bound it, an epsilon at argument. Again, if you've read first 4 chapters of Verschainen book, Standard Techniques. So yeah, the novelty is in the design of the algorithm in order to make the analysis easier. Skip these things. Yeah, sure. Yeah.
So even if the x, I mean, your x is coming from some sparse regime, but even if the x came from a convex set, by doing this AltMin, you can make the problem non-convex or settle at local minimum with respect to the dual minimization, and you can only settle at a local minimum perhaps, but yet your theorem somehow is able to go beyond and get close to the
Correct
optimal u star when it's coming from that family. So can you give some insight? How come you're able to break free from the issue of local minima settlement?
Oh, because it's a much simpler problem. It's one problem I'm talking about, right? So my go-to result, my wish list is actually what you're saying, proving general results for AltGDmin for a general problem. Somebody here asked me, can you study? Yeah. So that's my, eventually I'd like to do that, and that's actually an open question for future work. But for low-rank matrix recovery problems, the basic idea is you have a careful initialization that already gets you within a distance delta naught of the true solution, right? And then what you're actually, we could potentially be proving things here too by showing that my problem is locally strongly convex around that initialization and locally smooth around that initialization, right? So, and that's why there's classes of, so if you're concerned about one particular non-convex problem, you can say a lot more. Yeah.
One question. So when we were talking about the truncation for the initialization,
Yeah.
right, we did that truncation step where we basically zeroed out the large entries, right? So what breaks if we do like the normal, I suppose, understanding of truncation? Okay, just clip it at root alpha there.
What, so you are doing exactly that, right? Clipping it at root. Oh, you mean clip versus zero out?
Yeah.
I don't know. I've not thought about it. Am I clipping or am I zero? No, I'm zero. I think I'm. Wait, no, I am. I forget what I'm doing, right? I think it might actually go through. And it might, yeah, I see your point. Oh, no, okay. What breaks is the theory. Yeah. Algorithm-wise, I'm sure it will work because it seems like a better thing to do, in fact. What breaks is here we are assuming, conditioned on alpha being known, I'm assuming independent summands. There that, and then each summand, I'm not sure, theory might also go through. Let's talk about it offline though. We can look at the paper and talk about it offline. Other questions? Okay, so then we'll briefly talk about Byzantine resilience, and then hopefully I'll just introduce the three other problems where AltGDmin still is a good idea. Mostly for communication efficiency reasons. So Byzantine resilient gradient descent is a well-studied area. There's a lot of literature on it. One commonly used solution is the geometric median, which is essentially the vector extension of the scalar median, defined this way. So if you had a norm, two norms squared here, the solution, the argument you would get would be the mean. But when you don't have a two norm, you just have sum of two norms, z minus zls. then the solution is denoted by, is known as a geometric median. Now, this is not something that can be solved in closed form. There is iterative algorithms that exist to solve it, approximation algorithms with various levels of guarantee. Another solution that has been studied in the literature is what is called CRUM, which is find the ZL for which, essentially there's the most clustering around the ZL. So find the ZL for which most nodes data is close to it. All of these assume, of course, that the number of Byzantine or bad nodes is less than half. Just like the median needs that too. So here's what, again, existing work tells us about guarantees for the geometric median. It says that if you have these vectors Z1 through ZL, which are estimates of an unknown Z star, and suppose I can compute the geometric median exactly, then what I can say is that if most of this, if at least half of these, and I should have said Lbiz is less than half of L, if at least half of these ZLs are epsilon close to Z star, then my geometric median will be C epsilon close to Z star, with C, where C is a blow up factor. C could be 4, 5, 10, and that depends on how close Lbiz by L is to half. Right? The closer Lbiz by L is to half, the larger the blow up factor will be. Right? The more number of bad nodes that you have, the worse your result. And you can also get a high probability extension of this. All that exists. There's a paper by Minsker actually that I forgot to cite. And then the other thing is you can only compute GM approximately. Yeah. Now, Byzantine-resilient AltGDmin, as I said originally, is a very easy extension except for the initialization. Initialization is not easy now. I'll explain why. The rest, min step for B, as Chandra said, you can do it locally at the nodes, no change. The gradient step, again, each node is computing nabla L, its own partial gradient on its own data, sending it to the center. Center, instead of computing the sum or the average, is computing the geometric median of these vectorizing the gradient. So nabla L is n cross r, you vectorize it, compute the median, unvectorize it, right? That's your gradient, and then just do the gradient descent step, right? So that's it. Okay. So nice and simple. That's another free advantage of AltGDmin is you can apply. If you're working in Byzantine resilience, you can apply Byzantine resilient literature here. If you care about straggler resilience, which is what a lot of information theory people worry about, same idea, straggler resilient approaches for designed for gradient descent will directly apply here. Now, initialization is tricky because of the following reason. Recall that your initialization in the federated setting involves, I didn't give this in detail, but it involves using the power method, which is a well-known method of computing of singular vectors. A federated version of it is also well known for the initialization. Now, to deal with Byzantine resilience, you can do one of two things. You can either share all data with the center from all the nodes, and the center computes the geometric median of the desired matrix, and then you compute its singular vectors. Or you try to use geometric median in each power method iteration. So the first solution is very inefficient because you're sharing a lot of data. The second solution is communication efficient. It's actually the best in terms of efficiency, but it needs way too many samples. And the brief intuitive reason for that is that power method also starts with a random initialization. So at the very first iteration, your iterates, your estimates of U are very bad. So different estimates from different nodes will not be very close. And then the geometric median of them will fail. And then the whole thing breaks down. So our proposed solution is what we call the subspace median, which does the following, which says that you compute an initialization at each node locally and then try to compute their quote-unquote medians. But the U0Ls are closed in subspace distance, not in Frobenius norms. So you'll actually compute the medians or geometric medians of UU transposes, not U's. So you are gaining in communication efficiency, but you're losing in terms of computation cost at the center. But again, because, so that's your subspace median algorithm here. So node L computes UL, sends it to the center. Center computes the geometric median essentially, or geometric median in Frobenius now, and then finds the L closest to this geometric median and outputs that UL. That's it. Very simple intuitive idea, but basically this is the solution to Byzantine-resilient LR recovery for a class of problems that I'll talk about. So basically you get robust PCA for free, you get matrix completion, Byzantine resilience for free, using the same idea because the bottleneck was the initialization. And then what you can prove about subspace median is very similar to what you can prove about geometric median, which is if you have less than half bad nodes, and if for the good nodes UL is delta close to U star, then UGM will also be C times delta close to U star with high probability. And actually if you could compute the GM exactly, the probability of this happening actually improves from 1 minus P. Yeah, sure. No. For a small enough delta, yes, you need a small enough delta. Otherwise, anyway, delta always has to be between 0 and 1. But yeah, you need a small. No, I'm sorry. So, no, I think all you need is any delta less than 1. The result is meaningful if C times delta is less than 1. So, really, if you want a meaningful result, the result holds always. Is it a useful result? Only if C delta is less than 1. Right? And then you need delta small enough for the rest of the algorithm to work. So, if you want to analyze the entire algorithm, then often you need delta less than 1 over kappa square type of things. Good. Other questions? Yeah. Yeah.
Here the Byzantine nodes are the out of the, so if you could go back to the previous slide.
Actually, yeah.
This one.
Yeah.
So node L, right? Some of those nodes are Byzantine nodes here.
Yes.
And when you say argmin L in square bracket L, it seems that you're looking at the first L guys, right?
No, all of them. Big L is the total number of nodes.
Yes.
Yeah.
But when you say L belonging to
all else. No,
you're looking at one of the nodes.
I don't know which ones are Byzantine, right? If I knew which nodes are Byzantine, then I just throw away that data and I'm fine. Right?
And so here you're actually picking one of them, right? So you've computed L different GMs and you're picking one of them. Okay. And hopefully you're picking the one which is not a Byzantine.
That you can prove with high probability you are doing that. But as far as using the data of one node, actually even when you're doing median or geometric median in anywhere in all the literature, you're effectively just using the data of one node. Even though there's 10 good nodes, you're not, well you could go to median of means where it's slightly better. You could be using data from subsets of nodes. But basically that's the flip side of median is you can't use the averaging power of all the good nodes very effectively. Right? So if you use median of means, then your L-base bound goes from half to much lower than half. So you're trading, when you're using any form of median type estimators, you're trading reliability for accuracy. Or you're trading accuracy for reliability. Good. Other questions? We don't have to cover the whole talk. So, yeah, okay, good. Let's skip this. All it's saying is everything is nice. This GB is the heterogeneity curve. So different B star L's can be different at different nodes. So if they are too different, then your subspace error will converge only to that GB value. Skip the rest. AltGDmin for low rank phase retrieval. Actually, this is how this original work started. We were looking for AltGDmin for. So now the next 3 slides, I'll tell you AltGDmin for 3 other related problems. One is phase retrieval, which is low rank phase retrieval, where you don't have, you have absolute values of each entry of AKX star K, right? Same type of ideas with some modifications apply. Almost no novelty here given that AltMin was already studied, so results can be borrowed from there. This is interesting because matrix completion is an example of a problem where you can't beat AltMin in terms of speed because the problem, you're recovering from a subset of entries of the matrix. So it's column-wise decoupled and row-wise decoupled. So you could be doing AltMin for each row separately, which is efficient. You could be doing minimization for each column separately, which is also efficient. But if you look at federated settings, then AltMin fails basically. Excuse me. So what you can argue here is AltGDmin is the most communication efficient. Compute cost wise, it's as good as either AltMin or factorized GD. And the other reason for communication efficiency is there's one great data exchange step. So when you look at Byzantine resilience, it's a lot more communication efficient. For factorized GD, you'd be, first of all, I think the proof might even break down, but you'd be using 2 rounds of geometric median computation, so it becomes really slow. Right? And the main challenge in the analysis also, other than the fact that you have to use matrix Bernstein now instead of whatever we use there, is you need to also show incoherence of U at each iteration. You cannot impose it. So that's the main theoretical challenge. So this was a paper that just came out. This was with Ahmed Abbasi. And then a new ICML paper studies the Byzantine resilient setting for this problem and LRPR, where again, because of the incoherence assumption, you need extra steps in your gradient descent algorithm too. I'll skip the details. AltGDmin, as we speak, so we have this under submission to the latest ICML. You can also design it for the robust PCA and the robust LRMC problem. Here's robust PCA. S star is a sparse unknown matrix. So you want to recover X star from X star from the sum of X star plus S star, where S star is sparse. This is a harder problem than the well-studied problem so far because you have 3 blocks. You have U, B, and S. So the naive approach, which is to use Z slow as U and Z fast as B, S, will fail because you have to respect problem constraints. You need to have, intuitively also you need to initialize S first because there's no bound on the entries of S. It's sparse, right? There's no sparse outliers are actually by definition those which are large in magnitude. So you need a carefully designed multi-block extension of AltGDmin, which is hopefully topic for another talk, and then you need new proofs ideas too. Quickly skip the details. I can talk about this if there's any interest in MRI in the audience. I think not, but the main point is MRI image sequences can be modeled as low rank. They can be better modeled as a 3-level hierarchical low rank sequence, where the first level is just a mean image, second level is my rank R matrix, and third level is actually full rank, right? And if you modify the basic AltGDmin algorithm with just 2 simple ideas, first being that because some images are similar, you approximate the global mean and subtract it out, then apply AltGDmin, and then also do what's called model error correction to find the fine features in your MRI data. You actually get a 3-level method, which is still pretty fast, and with the advantage is it still has only 5 or 6 algorithm parameters as against all kinds of deep learning solutions. You can show, and we've done, I've had a whole PhD on this, Shilpa's PhD, that without any parameter tuning, the same algorithm gives the near best reconstructions for 25 different data sets, including prospective data sets also, while also being much faster than deep methods. Deep methods would, of course, beat it if you did application-specific model tuning and parameter tuning. So no argument with that. If you did your experiment so that you used one set of parameters for all brain, cardiac perfusion, abdomen, there's lots of kinds of imaging. What you do is you gain in average error and actually each and speed. Visuals I'll skip because again I don't think it's even for me I need to really zoom in to see anything. But the point is this has been done with an MRI collaborator on retrospective and prospective data, all with the same set of parameters. And end of this part of my talk, Always looking, by the way, for interested PhD students and or postdocs if there's interest. Open question is along the lines of what you were asking, which is AltGDmin for a general problem. Okay. References are provided here. Quick questions, if any. Yeah, yeah.
You have AltMin and AltGDmin. So, what additional conditions do you require from using AltGDmin? You have one theorem which requires mu coherence of right singular vectors, all these things.
No, that is needed for AltMin also.
So then, then what it is, because at least the way I see is that AltGDmin is a special version of AltMin, because the one way to do AltMin is AltGDmin. So it seems like you need more conditions for AltGDmin to work. So
no, you don't. Okay, when I understand, okay, that's a nomenclature. When I understand AltMin, I understand it as you full minimize over one variable, keeping the other fixed, and then do the other, right?
Yeah.
Whereas here, you're replacing a full minimization by one gradient step.
Okay.
Right?
Yeah.
So a full minimization over U would require either a closed form least square solution, which is expensive, or it would require a lot of gradient descent iterations to get a full U. But the point is you don't need all those iterations.
Yeah.
You could just do with one iteration and still prove the same kind of convergence guarantees. The number of iterations needed is a little bit worse. So there is a kappa factor. So there is something you lose by replacing.
Rather than complete minimization, if you take just one gradient, then you need more iterations.
You need more. So if kappa is this condition number, so if you treat it as a constant, then order-wise it's the same. That's why I qualify it by saying you get almost the same rate, not the same rate of convergence.
Okay. Yeah. Thank you.
Good. Questions? No? Okay. Then, yeah. No, I still have few more slides. Yeah. Yeah.
I mean, there's sparsity in the rank related domain. So you still do the B and the S, I think you call that as S. So you do alternative minimum.
I didn't talk about the algorithm at all. Let me talk to you offline about it. I want to spend 5 minutes talking about something else that I've been thinking about and looking at and working on in the last 5 years quite extensively, which is the state of math skills of our school students. And I guess this audience does not need a background on why we should fix our own and our kids or the world's kids' math skills starting in elementary school, because math is the most cumulative subject. Arithmetic, without fractions, you cannot understand basic algebra solving for 2 variables and 2 linear equations. And without that, all linear algebra and all of today's talk is of no use. And not just today's talk, workforce also needs, engineering needs, elementary, middle, a little bit of high school math. So workforce success, earning equity is the other reason you should care about math, because, most important, actually, yeah. And then math, we all, again, in India know that it's low cost and easy to teach, but instead of, I'm not saying we should not focus on STEM, but we should with AI coming in, and I've asked the question, why do we need to study any math? Well, you still need to know whether AI code is correct, how to deploy it, where to deploy it, etc. In fact, I'd go so far to say there's a renewed need to understand the math more, because the coding or the syntax can be done easily by AI. You could just know how to code in MATLAB and you're okay, probably, at least for many settings. So the question is, what can we all do? Because the education researchers don't seem to be doing anything about it. For a variety of, at least I have of course seen the US context more closely, but in all contexts, in all countries, there is math issues, Math could be improved for our students. So the question is, could universities be running tutoring programs, or could companies be running tutoring programs where the employees are volunteer tutors, or You have paid undergrads running sessions and graduate students or faculty providing tutoring to nearby schools. Or it could be run through any community group, for instance. And the second thing, again, which I definitely see missing in the US, but I'm sure it's not as well known. Maybe in this audience, of course, it's well known. That's why everybody's here, but not as well known widely in any country, is the need for early math. You still need to do your fractions by hand to understand algebra. You may never need to do fractions by hand because there's the calculator, the computer, the AI, the whatever, but you need to do it by hand to understand algebra, and then understanding of algebra is critical for everything any of us teaches or studies. Again, in the US, what is missing is textbooks have all but gone away, so the how is missing too. So I'm just hoping to start a conversation on what can we all, what is our responsibility as STEM and engineering faculty, as math-intensive STEM faculty, to make sure that, our planes fly safely. Plane flying software does not have bugs in it, for instance, again, for our own. So one thing I have been running at ISU with, and if there's cooperation from the schools, it's a very easy and a very useful thing to run, is a hybrid mode all year long math tutoring program, where you start supporting students early, starting in 3rd grade, and support them for as long as they want, and of course enroll students at whichever grade. The point also is that the students who start younger tend to stay because changing mindsets in middle school is very hard, as we all see with our own kids also. And then we also provide at-home math resources, which in the US context is an app, but it could be different for wherever it's run. The tutors are STEM graduate student and faculty volunteers primarily, and then 1 to 3 undergraduate program assistants for each site who manage the logistics and tutor. And they're often math majors, education majors, math education majors, wanting to be future teachers or not wanting to be future teachers. They just enjoy working with kids. The advantage I have seen, of course, the obvious advantage to students learning better, but tutors themselves tend to improve their teaching and communication skills often. Research communication, I've seen a drastic difference between a student's qualifier presentation, which made no sense, to his prelim presentation, which was much better formed because he had been tutoring for 3 years. And there's no good way to tutor. Our model is 1 tutor helps 1 to 3 students. If there's too many students, all of them could be in a large group and practicing on the app. Use of app is not essential, but it simplifies tutoring. You don't need to prepare problems. You don't need a very good tutor. And then, it removes the need for training also. Impact, again, we started with the younger students, where you see, it's also because there's, not too much difference between what an affluent 3rd grader knows and a not so affluent 3rd grader knows. It's very easy to change learning in 3rd, 4th, and 5th grade, hopefully for the better. I'm looking at Hari because we've had these conversations. Hopefully the CBR could be starting initiatives similar to this. And what you see is real growth. So from whatever data the local school district provides, you see more than 20 percentile points growth within a year or two if you start younger. And hope is, even if the students move away or whatever, at least you've built their foundations, so they at least have a better chance of understanding algebra. And if they continue, there is, of course, more people are willing to teach middle and high schoolers. Middle and high schoolers sign up but don't show up often. And then tutors benefit a lot, actually. We did a survey of tutors, but more than the survey, anecdotally, what we've seen is those who choose to tutor, it helps their mental health and helps them find their friends, helps them find extra faculty mentors, get reference letters that are stronger than the student took my class and did well, because you've had constant interaction with at least 1 more faculty member over your 4 or 5 years. And hopefully future teachers benefit by teaching alongside other STEM folks. The open questions, and this is the last slide. is something for us to influence education research. So all education pedagogy and all education research, a lot of that actually comes from US, is very short term because of data privacy reasons, student data privacy reasons, because of funding reasons, right? So there is a lot of research on removing homework from elementary and middle school because it's too stressful for the child. It is not equitable. But what this research, well, okay, and maybe there is some truth to it. I'm not saying that, India or China style homework is the best solution, but completely removing homework even in middle school basically means you are not getting any practice in your math. Other thing that is happening a lot is make math fun. Even trigonometry, which is a high school course, I've seen websites on how people try to make trigonometry fun, which can be done if there's infinite resources, but it costs money. Student focus time is very limited. So students will not stay focused for beyond half an hour. So the amount you can teach in half an hour if you're not doing real math is much lesser. So all of these ideas are actually good ideas, but taken to the extreme that most students are learning nothing in schools is what's happening, at least in the Midwest, in the US. And then the question is, whether or not we tutor, can we use the power of universities and our social media or our outreach people? She left, right? I showed it. Oh, she's there, yeah. So our outreach people to talk about the fact that math is essential, right? So we at least understand math is essential. In the US, it's called extension outreach. Universities have their own outreach or funding divisions. Or can IEEE talk about this? Just provide awareness, talk about math is critical for signal processing, or and how to country-wide, local, IEEE chapters could be providing this information. What are the good resources in Bangalore to improve your math skills? And then, there's a lot of other ideas, but that's kind of the open questions that I'll leave everybody with. And that's the end of my talk.
Thank you, Professor, for accepting our request and delivering a wonderful talk, and also for the insights, awakening insights. Thank you, everyone, for attending the talk. Our refreshments are arranged in the coffee hut. Please help yourself and continue your conversations there. Thank you.